Now we want to go through an example projectile step by step and kind of draw out what it looks like using our vectors. So we will use a scale on this. We'll use a scale of 1 centimeter equals 10 meters per second, and up will be up. So each of these locations, I'm going to label this is time 0, this is time 1 second, so as a projectile is in the air for 1 second. This is 2 seconds, this is 3 seconds, and this is 4 seconds. So this is our projectile. It's going to be projected up into the air as we go through this now. So on your paper you'll want to draw, starting this little tip right here, a box that is, or a square that is 2 centimeters by 2 centimeters. So if you need to pause to do that, go ahead. We're going to give this particular vector a horizontal velocity of 20 meters per second, so that takes the entire 2 centimeters here. So we have a horizontal velocity Vx of 20 meters per second to the right. We'll give it a vertical velocity of 20 meters per second, so Vy is 20 meters per second up. And then the resultant vector, since we're not actually lining these up tip to tail, when we draw the velocity vectors of an object in motion, typically we draw the vectors radiating out from the object. And so instead of going up and then tip to tail across like we did before to get to our resultant, we can simply draw the diagonal of the square here that we have, which is why we drew the square in this. And so this piece right here is the resultant velocity, or what I like to say is the velocity that you see. Right? You actually see the object traveling along this resultant vector. You don't see it going sideways and up, you see it going along in that direction there. So the projectile moves up through the air in this direction, and after 1 second, we're going to mark it here, it should be about as high as this little triangle over here. So you just kind of line up on your paper, right, where the projectile ought to be. And then we'll just do the same thing. We'll take a look at the behavior of the projectile now after it's been in the air for 1 second. Horizontally, the velocity should be constant, so it's going to stay at 10 meters per second. And then vertically we need to remember that the acceleration vertically is the acceleration due to gravity, or a negative. We use 10 meters per second per second. So that means this vertical velocity of 20 meters per second is going to change by 10 meters per second, and it's going to change by slowing down because our velocities are positive, our acceleration is negative. They're in the opposite directions, so we should get a vertical velocity vector of 10 meters per second. So you want to draw this all to scale on your diagram here. Again, pause as you need to stay up with what we're doing, and rewind as you need to. Again, maybe draw a little rectangle like so, right, that kind of matches those up, and then our resultant will be the diagonal right in there. Again, that is the velocity that you see. And you can tell by looking at it that it's shorter. So the projectile overall has slowed down. Horizontally it's been constant, but vertically it's slowed down, so the overall resultant is also slower. Move on to 2 seconds. Match up the object here with 2 seconds and this top triangle right here. So we had that drawn out for you. And again, at 2 seconds, what's going to be the horizontal velocity? Well, it's going to be constant. It's not going to change. So we're still going to have a horizontal velocity of 20 meters per second. Now, we've accelerated due to gravity another 1 second, and so we've lost another 10 meters per second. So it was going 10 meters per second. That means now our vertical is 0. And we know that from when we talked about free fall. At the top of the flight, the object has 0 vertical velocity. So the combination of the horizontal velocity of 20 meters per second and no vertical velocity is just the horizontal velocity. So the velocity that you see is also the same as the horizontal velocity. So unlike when we just threw something up in the air, it does still move, but in the horizontal direction. Alright, 3 seconds. Now it's coming back down. And so now it comes back down to the same height it was over here at 1 second. It still has a horizontal velocity of 20 meters per second. And vertically now, it was at 0. It's accelerating down at 10 meters per second. So now it's going to be traveling at a negative 10 meters per second. Again, our little rectangle will help us, and our resultant, or the velocity that we see right here, is the same length as it was at 1 second, it's just going in a different direction now. Continue on to 4 seconds. Object's pretty much down here near the ground, maybe not dropped below the ground like I have it here. And horizontally, still has a horizontal velocity of 20 meters per second. Right, this whole thing is before it hits the ground. Sorry about that. And vertically, it's going negative 10 meters per second, changing at 10 meters per second every second in the negative direction. So it should now have a vertical velocity of negative 20 meters per second. Draw your little rectangle there and a diagonal, and then there's the velocity that you see. Once we have this, we can try to trace out this shape. Should be a nice little parabola. And let's see how well I do this time. Not that great, but you get the idea. Follow a nice little parabolic path there. So you can try that too. Next thing we could look at here is, well, what is the range? Right? What is the range of the projectile? So as you can tell in your notes from the previous video on the projectiles, we can find the range by using our horizontal velocity times the time interval. So in this case, our horizontal velocity is 20 meters per second. So we're trying to find the range. 20 meters per second times the time interval. It took a total of 4 seconds. So this projectile travels a total of 80 meters. Remember, the seconds here will cancel out. And finally, we could figure out how high it went. And the easiest way is actually to think in terms of, well, how far did it fall, since it obviously went up the same distance as it comes down here. And so we can think in terms of our free fall. Displacement, right, is our initial velocity times time plus 1/2 the acceleration due to gravity times the time squared. And since we're saying just drop it, we have an initial velocity of 0, so that cancels out, or goes away, I guess, best way to say that. And we can simply take 1/2 10 meters per second squared, negative, include the direction, and our time that it took to fall was from 2 seconds to 4 seconds. That was a total of 2 seconds to fall squared. So we get 4 seconds squared times negative 5 meters per second squared. So I took care of that 1/2 here. Half of 10 is just 5. And our second squared will cancel out, and negative 5 times 4 is 20 meters negative because it went down. So our height displacement was actually 20 meters in this case.